a CNC torch table. We've done most of the 1-inch universal axis on the torch table. So you want to take a look at universal axis. And now, of course, simplifying this, to what we learned, and faster build, easier build, things like one thing like interior nuts. We're getting rid of like things like interior nut catchers where nuts can spin inside, make everything accessible. Yeah, dark and lovely.
Is that acceptable? Otherwise,
Yeah, I would prefer
light.
no.
You want dark?
Mm-hmm.
Okay.
We'll get used to it.
So, 1-inch universal axis prior work. So same as the 5/16 inch, the 8mm stuff. The concept is the same. It's you've got bushings around rods, and you've got the motor piece, the idler piece, the carriage. The carriage is what moves.
The green parts are the bearing, like carriage bearings.
Yep, those are 3D printed. So this is what we're going to be building an oversized. So motor piece, we've got the carriage, and we've got the idler piece. The idler functions only just to wrap the belt around and catch the rods and attach to the frame. So we can say there's 3 functions. The carriage provides the precision motion around the rods. It's where the belt is attached. It's where your tools are attached. So that's the part that's moving. So once again, 3 functions more or less. The motor piece, you've got the drive there. You've got the attachment to axis. And once again, you've got the spacing of the rods to be equal. So in all this game, like if we collaborate between the 3D printed parts and say the carpentry parts of wood, only thing we have to keep in mind primarily is the rod spacing so that the parts interoperate. If we get that right, you can make wood parts, you can make plastic parts. Here the design, initial design, it looks kind of hairy and complex. Like look at all those parts. And we've simplified it way over that. Like first we started with clamshells, and it's like all the bolts to put clamshells together. That was just a pain. So you've got, say like the idler piece, 2 clamshells, you got 4 bolts, 4 nuts, 12 pieces, well 9 pieces, 10 pieces right there. Well, reduce that to 1 piece, which is just 1 full shell. So that's some of the initial learnings. We thought this would be cool because then you have more flexibility in terms of taking things apart. But in practice, I don't know.
You don't want to take it apart. It's together.
Yeah, like if you're on an axis, you might as well, you don't really take off one part, you probably take off both parts if you're modifying something. So that wasn't highly useful. But the number of parts is remarkably small, that's all. So concept is very simple. You got a motor, you got a rod, you've got some bolts. Let's go through this so we understand how this is more. So we still have a motor, this is the small ones, but we're going to use larger ones. The ones we use are NEMA 26, NEMA 24. You look online, you can see they're slightly bigger than what we're used to. They have flanges for the bolt holes, and that's if we're going to make that out of wood, all you need to do is have a hole for the shaft and the correct spacing for the bolt holes. Now that's an industry standard, so you Google NEMA 24 bolt pattern and you can find that bolt pattern. And I'll give you the specific dimensions so you can do that. I mean, pull it up anywhere off the internet. So that's the kind of motors we have. The documentation right now we just started a thing which is called Large 3D Printer. So working doc, I'll paste this into the chat box for anyone who wants to get in there, because that is our editable doc.
Can you forward it to?
And then make sure that's open editable and find and edit. So yeah, working doc. I mean, we already Ken did some of these new pieces already. This is old. For example, this is your, what is that? That's your
It's the carriage.
carriage. Ream it out from the middle. Faster print time. Do that. V2. Good. Less print time. 3 hours 25 minutes. 0.6 millimeter layer height. 1.2 nozzles. So this is in FreeCAD.
I'm sorry, what makes that, you said faster printing? I know before you said something about the, heat.
We have 1.2 millimeter nozzles as our standard that we print with because we want to print larger things. Typically, the hobby printers use 0.4 nozzles, so you get much faster print rates, which go as squared. So it should be, in theory, you'd be printing out 9 times as fast because of the 4 compared to 0.4 compared to 1.2 is 3-fold factor. And it's pi r squared for the area that you're depositing at one time, so it's 9 times in principle faster. We're using still our regular heater block. We're not even going to a thing called the Super Volcano. We have that, but let's get this to work first before we add any variables. The goal for now is get the large frame, large axes, working, including the lifting of hundreds of pounds on a bed. Talking about the bed's going to be heavy. If you're talking about a full print, you talk about a module that's 200 pounds. That's what we do. Plus the bed weight, it might be another 100 pounds. How much can these motors do? They can do 50 pounds a pop. We have 200 pounds out of the box with 4 motors. So that's a basic design we start with.
How are we gonna do a bed that size that's rigid and not 200 pounds in and of itself?
Yeah. Let's get some.
Because to your point, the frame's gotta be larger than the bed, so the bed itself is what's gonna be 8 by 4.
Bed. No, bed is going to be 4 by 4.
4 feet by 4 feet.
We don't have to go that far. We can do that. How do you do a large bed like that? Let's talk about that. That's some way. But let's get to that in a sec. I mean,
yeah.
you can. I mean, so you want to do reinforced flat plates. So steel plates will be quite warped, but you can make it more straight by welding on thin honeycomb structure on the back. Like for example, on D3D genealogy, we did that where you reinforce it by welding a pattern across. So anytime you have a weld that's at a right angle, you get it super straight. If you clamp it down with a flat bar lengthwise, if you look at the 18-inch bed printer like those, how do we do the bed inside? The 18-inch bed right here, how do you do that bed? Build pictures. Bed pictures. So that's the bed here. Let's take a look at the bed. But what you do is, well, that's the large steel, but what we do is then weld this. That's how you reinforce it on the inside.
Okay.
And therefore you can get a relatively lightweight structure. Now here we can use our halogen heaters. So that's an improvement. We filled it with foam and ran the nichrome heaters, which are much harder than the halogens. So we can do something like this. This was only 18 inches. We have we have a plate that's 3 by 3 feet. If we want to go 4 by 4, we'd have to cut that out of the large sheet we have.
Just one question, not being pro at welding or anything. Does one have to be careful of warpage or something from
Well,
your
here's
weld points? or
So
Does
what
that
you do
happen?
here is when these are, you hold down these bars, which are stock material, that's 2 by 1/16 lightweight stock. That might even be like, yeah, that's 1/16. When you hold it down
Mhm.
really flat, that edge is quite straight, like to within like
Yeah.
a millimeter or so. So you'll have a millimeter flatness across the whole thing. As long as you do that, like once you're connected, cool. Just the tack welds do it. Like if you just burned a lot into this, yeah, I mean you start warping all this. This is sheet steel, so
You can turn down your voltage, right?
yeah, you can turn it down. But if you get that entire thing hot, it'll all warp on you. So you want to just weld it this style where you
Tack
just got
weld it,
dots. That's plenty strong for what we want to do.
Is the reason why the bed is so thick? I mean, is it for insulation, or is a lot of insulation going in there, or?
Yeah,
I mean,
the reason for that is to keep structural integrity.
Mhm.
And the second one is to insulate it, so you're using about 30% less power with an unheated chamber. So we took some data, and that saves you about 30% energy on a heat bed, which if you're in production, that matters for numbers and cost of electricity. If you're running a farm that's got a bunch of these and running 24/7. Now, what are other ways to do it? How about tile, 4x4 tile or 2x2 tile, super flat.
Ceramic tile.
Yeah, like for flooring.
Yeah.
That's a good idea. So we can put the,
What would
the
you-
heaters.
And do
It's
that on
heavier.
the same substrate.
You can put it right on this.
Yeah,
Yeah.
that's what I'm saying. This is the substrate.
That would be a good idea.
Yeah.
Can you show a picture of the tiling? We also
Just
use
like
it for
ceramic.
The just
Like-
I got it.
We're gonna use this.
Yeah.
We're gonna use
So-
the same frame. So
Okay, so what kind of insulation is gonna be able to take that extra heat?
not insulation. You design it so that the heat dissipates and you got a water cooling. You'd have to have water cooling in that place. So we're gonna, like this frame, it's gonna be our multi-purpose prototyping frame, and we can use it for the subsequent CNC experiments. Like for example, the MIG head, we just replaced the head and put on a torch head. With that, if you want to do production, like hour-long prints, yeah, you'd have to have water running on that, because your entire printer would have a meltdown after an hour or so of heating up. You see how hot that stuff is. So that's the bed style. That's the technique. Talk about larger beds. Here, those individual squares are like 9 inches. So if we do like every 9 on center, that's pretty good stability. It's like having an 8x8 bed, somewhat like on the D3D Pro, the other printer we have. Yeah, like every 8 inches to 12 inches, probably like less than 12, like 8 to 9 is about the right number. So you have complete stability, like in terms of flatness. And the way those are intersecting there, just notched out one into the other, so they intersect like that. You can grind them down like that. That's the bed. But the design is like, one of the main design considerations would be like how much, you gotta start thinking, okay, how are my motors gonna do for lifting that bed? That's a challenge, right? So,
That's why you have counterweights, like on this.
yeah, like on that we have counterweight, so we should do counterweight too. If we have 200-pound lift capacity and our bed is under 100, we could do it. We could just test it without it and then maybe add those later. But we wouldn't be able to do our full prints on that. We'd have to add those counterweights later. And it's a pretty simple mechanism. It's we would probably use like, what's it called? What's like this tent wire, or what's it called? That strong wire paracord. Paracord works well. You want to have bearings around that so the paracord would slide well. But one of the main limits is design of bed weight. So I mean, each motor does 50 pounds force. You can calculate that from the torque of the motor and the diameter of the pulley. The pulley is still 1/2 inch diameter. So we're using the same as on the 3D printers. But that turns out to be 50 pounds with the motors we use. So the kind of, yeah.
I mean, is it pretty easy just to add in a few more in series?
Yeah.
Yeah.
But the Rams
Yeah,
cannot
but
take
it's so
that,
much,
right?
it's easy, but it's all time, right?
Yeah.
So in 3 days, 4 is a good number. You can go higher, but then it becomes like so much. It gets kind of too much
Yeah.
at that point. I mean, 4 is perfectly workable. You know.
Are we using the Rams board or?
Yeah.
Okay, that's possible. Okay.
Yeah, with the universal controller.
Okay.
So universal controller for control. With external stepper drivers, the little drivers are not going to do it.
Okay.
We're going to use external ones. Universal controller. What's that look like? Let's put a link on that so you can study how that was done there. So anything with blue outline means a hyperlink. So you can click on that. Then the hyperlink pops up. Universal controller, that's another page. So we build upon this. Universal axis here, so that's a critical link. Let's go over the pieces, and then we are clear about how this thing works. So just studying the simple universal axis does it. We know we have a motor, we have a pulley, we've done it. You guys have done it. You got a set screw and a pulley. That's it. I mean, not much to it. It's larger shank on the motor. It's now, I think, 8 millimeters. So here it's like 5. We go to 8. The bearings. Now we go into steel, brass bushings. That's all McMaster car. So if you go to McMaster, you can get the 1 inch. So you would look for 1 inch bronze bushing. You get stuff like this. These are like, yeah. There's all kinds of types. All embedded sleeve bearings. They're kind of self-lubricated. That's what we get. You get them in all kinds of sizes, and 1 inch is very common. So this kind of a thing. Well, let's get a specific link to this, and it's only. What are we doing? We're doing 1.5 inches long, I believe. No, not like that. You have different wall thicknesses, so what you want to search for here is inch, and then for shaft diameter 1, and then you have different wall thickness. We're just using 1/8 wall thickness, so it's kind of thin. 1 inch shaft, so this one we use is 1.25 OD, and it's this one, I believe, here, which is 1.5 inches long. So you go to product detail, it looks like that. The cat is here. So it's 1.5 inches. So therefore the carriage has to be a minimum of 3 inches to hold these.
Because you put 2 per side.
Yeah.
So it has a flange, I guess. Must be.
No flange.
No flange. Okay.
No flange. We've got a bunch of these. And that's industrial grade. That's going to be very strong. It's metal. So that's the equivalent of the plastic 8 millimeter. What's next? So this is the belt pegs of before. Now we have the belt clamp and the belt cylinders. We need to print new versions of that. So that's printing. So you got your pulley. This bearing for the belt, what we can use now is use the 8 millimeter shaft, which is common, which we use elsewhere, like on the universal printer. Use it as a shaft for a 3D printed pulley, just for the idler. So you just gotta wrap it around. So 2 bearings on the outside, shaft through it. So if you're doing your wood block, 2 bearings, shaft through, 3D printed piece to spin on that.
Could we do that with metal instead of wood? Just wondering.
Sure.
Yeah, if you wanna drill
Just
metal.
give it a try, perhaps.
No?
Hmm?
You want,
Yeah,
don't
just
have the time.
trying it out, perhaps, if we get the time. Yeah.
No.
No.
No, we don't have the time. In
Okay.
3 days, we're gonna,
Okay, gotcha.
let's not do it, okay, so the
But in
psychology
principle,
here is
it's
we got, it's doable,
it's
completely doable.
Okay.
If you wanna go more industrial grade and have a print, that would be more appropriate for the, say the MIG welder printer,
Totally.
which, just the radiation would probably melt down your parts after some, so you gotta shield them, so metal would make a lot of sense. But, like right now, 3 days is extreme, we don't have time to mess with stuff, we'll be glad to, finish everything, right? And we've got 7 axes, like 8 feet. The rods are like, you carried the rods, how heavy is 1 rod? 2 of those, 1 rod, almost 1 rod is used for 1 Z-axis. It's heavy, right? It's
Definitely.
heavy stuff, so let's not, no room for like anything outside of mission critical.
We're using 1-inch rods, right? Not
Yeah,
those
1 inch.
huge, okay.
Now, we also got hollow rod, so we did get it from McMaster Carr. Hollow stuff, which is 1 inch OD, and then it's 1/8 inch wall, so we can use that for the X and Y to make that part light. For the Z-axis, those rods only come like up to 6 foot length, so we can't do Z with it. I would like to do it because I mean these rods are getting heavy. I mean talking about 9 feet. What was it, like over 100 pounds just for the rod? I mean, so the constraint on the 3D printed parts is just strong enough so you can hold the weight. I mean, it's literally the weight. Now you're gonna have the heavy bed, but you have 4 of the Z's, and you kind of need them. But that will be the heavy part. What I would suggest actually, when we build the structure, we can hang the XY gantry at a comfortable height. Because actually, like, if you hang it above your head, that's actually not comfortable. We should just start it like 6 feet, whatever. We can mount it higher later because the system will be completely remountable to a higher position. But just for comfortable working height, we'll build a large frame, but let's work comfortably so we don't have to like go up on ladders to actually mount the axes and stuff like that, just for ergonomics and getting this thing done, because we can easily hang it up later. In fact, it would be good to prototype it at comfortable level so we can move it, because I mean we'll be messing around and getting tired and stuff, so doing that. Okay, equivalent of so you need 4 bolts for the motor. Now the motors are flanged in this case if you go to this, so it's not so you can go all the way through. The bolt length doesn't matter, which is a good thing, so you can use any kind of bolt length. Like you don't have to have a very precise bolt length. In here in the universal axis, those are very precise length. They're 25 millimeter bolts because we're going right through the plastic and threading in. So that's that. Then you've got 3 pieces still: the motor piece, idler piece, and carriage piece, and a belt. The belt is wider; it's 15 millimeters now. So instead of 8, what is it? No, it's 6. Instead of 6, we've got 15. But other than that, same concept, just supersized. We did this. That's the kind of topology we got on a. This is like not good enough. Like the rods bend enough that you can do this, but very marginally, so you don't get good quality out of this. You can hardly lift. Like we couldn't lift the bed properly. Like it started skipping with the smaller motors. Now maybe if you want to do this and then use heavier rods, the thing that started bending on you was the actual x-axis. I mean, 4 feet wide
And just
with the
hammocks on
yeah,
you.
it just starts to bend, which does work because of bed leveling. That corrects it. The Z height bed levels. It corrects it for you, but you have to print like just you won't get the high performance of going fast and stuff like that.
They can't see your example.
Okay. am I sharing? I'm still sharing
Yeah.
what locked up there.
Yes.
Maybe stop sharing and start sharing again.
Is it different?
Yeah, it's different. Yeah.
There you
There we go.
Yeah.
So in this configuration, this is what we're doing, this supersized 1-inch rods. So 4 Z-axes, motors on top or bottom. Now since I would actually maybe mount them on the bottom because you got all the wiring to go up there. Maybe just mount them right on the bottom so you have shorter wiring. The universal controller is the other part. But yeah, think about this. We actually have that print surface there. We can reuse it if we like. It's 3x3. It's sizable. That would actually be a cool thing. I mean, we can go to larger if we want, but I mean, I'd be happy with getting this to work.
And
Um,
to confirm, when you were talking about the weight specifications or requirements, if each of these motors is limited to 50 pounds, I don't know how much the rods support, but does that mean that the part has to be limited to 50 pounds, or is there additional weight distribution of some sort, or are you always limited to like one axis and one motor?
so you got 4 of them, so you're limited to 200 pounds total lift ability. So you have
Which
to use
we end up
counterweights.
almost in rod. I mean,
We're gonna use hollow rods for so the Z rods don't count because you're not lifting the Z rods at all.
oh, okay.
What counts is the Y rods, and for that we have hollow rod,
Okay.
which helps. So that hollow rod may be like, I don't know, maybe like 30 pounds, 20 pounds. So we still have, like if we do a lightweight bed like this, we can still get it to work without counterbalance, very likely. Because 200 pounds, that's considerable. That bed there, it's about 45 pounds without the the honeycomb on the back. But the honeycomb on the back could be light. That could be like 5 pounds or 10 pounds. And we could put something lightweight like a mesh on the bottom, and that's full steel. What we want to do is hold a little bit of insulation and the lamps.
Gotcha. Hmm.
So we should use probably like 4 lamps, 4 to 8 lamps. We could use 8 even for 2,000. 8 is only 2,000 watts. 1,000 watts would be plenty to heat this up because they actually work really well. They're actually much more efficient than other means because they are radiant as opposed to conductive heat transfer, which is faster and more effective in this case.
On that note, not to derail too much, but in the future, if you did want to have a 3D, a metal printing head, is there a way to use, higher wattage or just multiple halogen lamps to melt metal as well?
No, halogens go only to like, what, 400 watts metal. Metal is 1,100 to start.
I thought there was
Oh, it depends what metal. You have low temperature metals that melt at 200 or 300.
I thought there was some like higher
But
wattage
those are not
halogen
chemicals.
and even halide lamps. I guess that could do like up to 2,000 Fahrenheit and stuff like that.
I don't know. That would be news to me. That might be the filament temperature, but the radiant energy temperature, I don't know, maybe it's true. The only way I know that you can do it is for melting metal is induction, not photons, but electromagnetic radiation. I don't know what's the limit of a photon. You are talking about laser. Lasers, yes, definitely melt metal, but I'm not sure how much a halogen gets. But
Yeah, I can't look it up right now because
Yeah. That would be interesting, but I haven't heard of it. Doesn't mean it's not possible, but the thing you have to pay attention to is heat loss. Maybe if you have a very well insulated chamber, then you can do it. But then again, if the halogen goes to 2000, when does your glass melt in that?
Yeah,
You can melt the glass
there's
before
all
you melt
sorts of
metal.
Which glass? That's
Of the
is
gold.
Halogen
silicone.
is a glass tube. So what's the higher melting temperature?
Oh, they're the- I was gonna say they're-
Glass or metal?
But they're the, I was,
How do you mount the halogens around the nozzle to melt the metal, right? Like,
Yeah,
that just seems
no, it's a
simple.
different
I
problem
think that's
beyond the scope of this mundane
Yeah.
pedestrian discussion here.
Getting back to the weight, I was wondering, the printed part also, is that a concern? I mean,
Oh,
if
yes.
you do it massive part? Or?
Yeah, a door module is gonna be, or a wall module, they're around 100 to 200 pounds. If you print a full stack of 2x4s, you're talking about a ton or something like that. If you print a 4x4 bed of 2x4s, that's like a ton. So yes, that will be a huge issue. You can't do the full bed. You can only do a part of it, or hollow shapes, because what's a cubic meter of plastic weigh? What's the density of plastic? It's like 1 gram per cubic centimeter.
and would one tend to print like completely solid or like a honeycomb
Oh, yeah.
structure in the plastic or
Yeah, that's the advantage of 3D printing.
Yeah.
If we do the 2x4, do it honeycomb to save material, while getting you the strength that you need. You
Yeah.
can print it full for full strength.
Mhm.
But with honeycomb structures, no, you don't. You might not need to. You can optimize for geometry,
Mhm.
for strength to dimension ratios.
Mhm.
So plastic is about a gram per cubic centimeter, or in other words, a ton per cubic meter. Oh, we've got more than 2 cubic meters here, so that's 4,000 pounds we could print on this bed. We're talking serious stuff here. You're not going to be able to counterweight that unless you have an extremely precise counterweight system. No, you can't. I mean, the motors you got 200 pounds in the motors. You need to, well, what you can do is gear down, but then the belts. You got to go beyond these belts. They're 50 pounds, safe working strength,
gotta go to chain, no? Probably.
chain. Hey,
Or
we're
have a
we
picker
got space
place
with chain.
We
could
could,
pull off
could you use water tanks
parts.
Well, yeah, you could do.
for the counterweight? That
Sure.
way it changes while you're.
Oh,
Water
yeah,
tanks?
Look at that. Yeah. Okay. So there we've got a
So
smart
flood the
idea.
bed?
So water tanks that get emptied, and then yeah, you could possibly, if you design this
Right.
extremely well, you can probably use these motors because you got 200 pounds of force. You only have to have enough to have a differential of force to counteract the friction of your weight. So if you got less than 200 pounds of friction in the system, yeah, you could do some kind of a counterbalance system, a more funky one, beyond the scope of this pedestrian discussion.
I don't know if you Google halogen bulb heat output, if you get the same thing I do, it answers the question on the bulb in the glass and the heat output.
Yeah.
I don't know if it's freezing again, but it's saying the bulb.
Yeah, this is the filament. So you have to talk about how that filament, what's the temperature once the, because the radiation is omnidirectional, so what is the actual temperature it's generating a certain distance away? It's not going to be that high, so that would be that at the filament. So if you could have a metal very close to that, yeah, you could melt it, but how does it scale to, you know, if you got bulbs, I mean, you got to go into the metal too, by conduction. I don't know, maybe